Welcome to Create Part Libraries with DriveWorks, and today we're going to discuss the numerous ways that we can leverage DriveWorks' unique technology to build parts, assemblies, drawings, and even documents to transform the way that we work inside SolidWorks. My name is Jordan Kleinschmidt. I'm an application engineer, certified SolidWorks expert, and certified DriveWorks professional located here in Minneapolis, Minnesota. I've been with GoEngineer a little over 4 years, and in my time, I've developed quite the resume. I've worked mostly towards design automation, and process automation through DriveWorks, but I also specialize in costing, imported file conversion, weldments, and a few more. And when I'm not at work, you might find me playing disc golf on a nice day, or maybe I'm in the workshop. I consider myself a maker. A creator, and where that I could be in the workshop, and that could mean anything from my home office to my garage to my kitchen. And I just want to really start today by setting up our agenda before finally covering what we'll talk about today. So if you're new to design automation, I'll give you an introductory overview of automation within SolidWorks, and if you're not, this should still be as a good refresher. We'll cover the methods of automating CAD models in SolidWorks and DriveWorks, and we'll also take a look at some of the strengths and limitations of each. Then we have loop model generation. Here we'll leverage design tables in a completely different way than you might be used to in SolidWorks. And if you're new to DriveWorks technology, just wait until we get to generative assembly modeling. This is so completely unique to DriveWorks, and it exponentially pushes the boundaries of where design automation can go. And we'll use it to generate and assemble data that is uncaptured. And just when you think you've seen it all, we'll also use DriveWorks to automate the generation of product documentation, which can be also generated in mass or on demand. And before wrapping up, I couldn't end without talking about the integration capabilities of DriveWorks that make it a must-have for your own system automation. So what are we waiting for? Let's go ahead and jump right in, starting with design automation basics. Now, whenever we want to automate a design or even a process, it's all about repeatability, and we want to have designs that you may have heard us say that are similar but different in nature, that are rules-based, where we can assign some behaviors to our documentation, our parts and products. There are several techniques of automation available. A couple in SolidWorks are rules-based automation and master modeling. Then we'll talk about a third option here, which we'll leave as a surprise until we get to talking about what DriveWorks is. And finally, we'll talk about the ways that we can automate SolidWorks files. So not just techniques of automation through CAD in general, but how do we automate in SolidWorks specifically? So 4 techniques of automation, the first one being rule-based modeling. I think this is maybe what we're familiar with when we think of any sort of interdependencies between dimensions. So this could be where one dimension is equal to another dimension or is equal to half of that dimension, or it could be things like if statements, where if a value is 0, then we'll suppress these parts or we'll unsuppress them based on whatever it is. But for the most part, the whole idea about rule-based modeling is that we have a small input and we get a larger output from those parameters. So I might only have to type in the overall length, width, and height of my component, but the output of that typically generates much more than that. And then we have master modeling, which allows us to basically save this file out as a copy. And now that we have this copy here, we can modify its configurations and change dimensions without changing the master itself. These can be rule-based as well, meaning that we can have master models that still have the same rule-based design technique inside of it. We can suppress parts and we can suppress features, and oftentimes we'll save it as a unique file name, we'll package all that up and save it in a default folder. So, well, master modeling can have rule-based design inside of it. it doesn't work the other way. Rule-based design isn't necessarily master modeling. So these are the two techniques of automation that we get with just SolidWorks alone. And when we're automating through SolidWorks, there are several different ways we can execute that through SolidWorks embedded processes, through Excel, or through DriveWorks. In the SolidWorks embedded processes we're going to look at will be things like the equation manager and the embedded design table. So taking a look at each one of these, I really want to show you the strengths and the limitations of each of these through what's called a SWOT analysis. So first, what is a SWOT analysis? Well, it's an acronym that stands for strengths, weaknesses, opportunities, and threats. And the strengths are the characteristics of a product or a something we're analyzing that is internal and helpful to us. Weaknesses are harmful internal characteristics of the product. Opportunities are external helpful characteristics, and threats, well, are external harmful characteristics. So if we apply this and we take each of these methods to automate in SolidWorks, we can analyze the strengths and weaknesses and sort of pit them up against where we can leverage our design automation. The strengths in the equation manager is it allows us to use rule-based modeling as well as master modeling, and also allows us to use what is called input-based generation. So we have an input and we generate outputs from that. We have some sort of form that acts as a form that I can put inputs in and generate my model rules, my outputs. Some of the weaknesses with the equation manager, though, is that there's not really many Boolean operators. We don't have a whole lot of functions built into the equation manager, and the formatting leaves a little room to be desired. Opportunities in the equation manager can be paired with configurations to drive unique equations into each configuration. And threats to using equation manager is the risk of broken equation references that could end up causing dimensions to be dangling and needing to be reattached. We also risk lost data if we don't export our equation manager because we could corrupt our files and we won't be able to get that equation manager back if somehow we wake up on Monday and the file's not opening with that corrupt message. So make sure that if you are using this method that you are exporting your equation manager. But there's also a lot of tribal knowledge in that equation manager. I've seen some very long, lengthy equation managers and nobody can understand it. There's only one user who knows how this works. That's what we want to avoid in using this tool. And then we have the embedded design table. The embedded design table is default in configurations now, but the automatic creation is part of its strength. They allow us to rapidly create configurations, and the table itself is really easily understood by many. So with just a little bit of interpretation, a user can hop right in and start configuring. The weaknesses of this is that adding the data is inefficient, and the formatting, again, probably leaves a little bit of room to be desired. Opportunities to take advantage. There really are none here because this is embedded. We can't export this in any way. So accessing this externally is really not possible. And for the threats, however, we could potentially increase the size of data by adding too many configurations, too many details or small features. There will create large data sizes, thus impacting our performance. And of course, risk of data loss if this file was to be corrupted. Some of the weaknesses and threats based on the embedded design table are answered by some of the strengths and of Excel design tables. The strengths of Excel design tables is that rapid data entry and the ability to use Excel functions to generate the data. We can also use configurations or we can also lean on configurations to build our similar but different models, and it is also work nicely with an input-based generation. Some weaknesses, again, are excessive file size, but uniquely to this one is design change. It's hard to make a design change because generally Excel design tables are set as a one-way street. We have to update that dimension in the Excel design table, unless the setting is turned on that allows that two-way communication. Some opportunities to take advantage of here is things like the configuration publisher. With Excel design tables, we could use a configuration publisher to essentially build a form that we would be similar to seeing in DriveWorks that has all of our inputs. We just select which inputs are what, and it'll find the corresponding configuration and populate that. So that's a really nice opportunity to enhance your Excel design tables, but we're still at risk of data loss and poor performance. And that's why DriveWorks Pro really was created in the first place, to address some of those limitations that we have in SOLIDWORKS day in and day out. The strengths of these are plenty. Unfortunately, I could only fit 6 or 7 on here, but we can automate parts and assemblies, but we can also automate drawings too. That's something that SOLIDWORKS could never do before. It's great with rule-based modeling, and it's great with master modeling, but now we have this other term called generative modeling. Now, what does that mean? We'll cover that in the next slide. We can generate documentation, so Word documents, HTML documents, emails if we want. And it's great with input-based generation, much better than other solutions because we have advanced form controls that allow us to drive our change. And strength of this, again, is performance. Because we're using master modeling, we're saving these as files. These files will be optimized because there's not a bunch of suppressed configurations hiding inside of it. Some of the weaknesses, some additional upfront costs. With any automation, you're going to have those upfront costs, but we'll quickly see an ROI on those costs based on the automation that we build, and we'll talk about just how much at the end of this, and a high learning curve. But really, those are really the only weaknesses I could come up with, and I might be a little bit biased, but I am honest. With opportunities, we can have opportunities for web integration, so building this into our websites to allow additional users to configure without needing a SOLIDWORKS license, without changing the modification of rules. There's a lot of opportunities to grow with DriveWorks Pro. And finally, threats. Again, had a very hard time finding any threats, external harmful side effects of DriveWorks Pro. Let me know if you can think of one for those of you who are DriveWorks Pro users. But yeah, I'm drawing a blank there too. So amazing strengths with very little weaknesses, what we can expect with DriveWorks. So now there's this third automation technique that I promised we'd cover, called generative modeling. What this is a method of design automation that helps us to construct assembly models or part models without requiring the master model to be captured. So normally when we go in and generate a part drawing or a part in DriveWorks, we have to capture the data. We have to build a form that makes it look all nice, and then we have to write model rules to it. Capturing the data, though, can be time consuming. What generative modeling allows us to do is, in theory, insert an infinite amount of components that are uncaptured based on rules, inserting components, working very similarly to how a regular design engineer would build a regular model without requiring a master model. So to illustrate that a little bit more, we have our third generation task here. All right, it's like as if we were to look for a file in a model. DriveWorks will search for the correct file, we'll narrow down that file, and we can insert that into the model without it being captured. Size and scale the model as necessary. And we can even loop these tasks as well, inserting the same components or different components over and over again, sizing and scaling those until we tell our loop to stop. So very awesome capabilities here with generative modeling that makes master modeling, the limitations of master modeling, well, really limitless. So we have rule-based design and master modeling. Now we have this third sort of umbrella, we're generative modeling, where we can use both master modeling and rule-based design inside the generative modeling platform, but we also have all these other tools at our disposal to generate those models. So that's a lot of the theory. I promise I'm done with theory for the rest of the day. Well, maybe a little bit more theory here and there, but regardless, let's go ahead and talk a little bit about looped model generation. So looped model generation is a way that we can generate models automatically without while using a design table. So we're going to generate all of the possible models in a sequence. How we use loop model generation, it does require a module called DriveWorks AutoPilot. This is a paid module, but it's absolutely necessary to make sure that you're saving the maximum amount of time with your workflows. DriveWorks AutoPilot is a DriveWorks Pro module that automatically processes our model and document queue. So we have this always running in the background on our server computer, and this will generate all the models so that I don't need to manually go in and release each model until SolidWorks switch to make. AutoPilot takes all those issues away from us. So let's go ahead and do a test of looped model generation with this blind flange. Now, this blind flange is real data coming from web databases to generate many of these flanges, and there's actually 117 total. There's some parameters that we want to drive about this part. For example, we might want to drive the description or the vendor part ID or the class of this flange to things like dimensions, like the nominal pipe size or outer diameter of the flange. All of these are provided by my vendor in the vendor data. So I basically just copy paste their data and put that into an Excel sheet. The file name will follow this nomenclature, BF for blind flange, followed by the class number and nominal pipe size. For the file location, we can also automate the file locations and where this file is saved. This is such an underrated function of DriveWorks, and just constantly placing this in the same location every time. So maybe I'll have a spec sheet in one location and I'll have my parts in a vault or some other area where I keep all of my parts or my drawings. And so what loop model generation is going to do is every time that we process a model, it will read this first line and assign the values to the model rules by just looking at this table. And once that model is released, it then looks at the index and just cycles through each one of these rows until there's no more rows to digest. So what does this look like in the grand scheme of things? Here I'll open up DriveWorks Administrator to show you just that. So the first thing I want to do is I want to add that table. Let's first make sure I'm in the right project, So I'm going to go ahead and add this table. It's just an Excel data table. So I'll go in and give it a name, do what I need to do there. I've already created this table though, so we'll just go ahead and take a look at how that imported. So what's nice about these tables is that it's not super finicky about where the data is, whereas if we're using Excel-based design table, we have to format things very specifically to make sure that it works. Here, I can more dynamically control the cell that's going to be referenced, so I can have a lot more control over my Excel design, or over this table than an Excel design table would be in SolidWorks. Now that I have the table built, I want to introduce a constant called loop constant. So when adding this loop constant, this is just going to increment every time that it releases a file. So our loop constant can be set at to 0, or it could be blank if you want. I like to set it to 0 so that my model rules will read in nicely. Now that I've added the constant, I'll go into my model rules and I'll build the rule here. You can see I have several rules that look pretty much the same, and this format is the same for really every rule. All it's doing is it's looking up the cell from my constant. So let me go ahead and add maybe a vendor number. I'll use the VLOOKUP function, which will look up a value in my table corresponding to the match found in the first column. So for the value, I want it to be my index value, which will be my loop constant. And for my table, I want it to come from my flange table. And for my column index, I want it to return the second column value found here. So it's going to look at this here. It's going to see, okay, well, this is a 1. Let's look at index 1. And the first part here in this table is the vendor part number 2, which is BF15005. All right, and that rule is the same, just kind of sort of adding 1 to each new column that I'm referencing in the description and the outside diameter and so on. You'll see sometimes these rules like DW variable NPS, it's just me saving this as a variable so I can refer to it in another description property or whatever it might be. But these are all just really saying the same thing with the VLOOKUP and the same loop constant, same table, different column. So once we've linked all of those, the next thing I'm going to do is introduce a macro called release parts. So when we add the macro, release parts here, or release models, we want to release the actual CAD model. So we'd find that and drop release models in through there. Then all we're going to do is just select the only flange model that we have captured in this project, just blind flange. From there, I want this to loop, but I don't want to press the button to make it loop. I actually want to loop as soon as I generate, as soon as I hit generate. So I'll go ahead and click edit, and you can see that I've built this macro in a loop. So if we take a look at this here, let me zoom in a little bit. There we go. We're going to select my macro name, which is release parts. We're going to select my counter constant. Our increment can stay at 1. And then for the limit value, what I want to do, let me zoom out again, is basically count the number of indexed values there are. So the index 1 through 117. So essentially I want the maximum value in the index column. So I'll do a max, table max, and I want to search my blind flange table, and I want to return the value in column 1, which is 117. Okay, so the 117 different components are being built. Since I don't have time to generate all of that while you are watching, I'm just going to set this to 3 for right now, and we'll watch how DriveWorks will rebuild this here. So I want to make sure my AutoPilot is running to start. You can see that it is started. So I'll go in and click new, and we'll just hit generate from here. Let's go ahead and look at SolidWorks now. And it's not only going to build the parts, but it also has the rules to build the drawings, to scale and reposition the drawings to make sure that they're within the constraints that I've defined. Now, I probably could have spent a little bit more time making sure that the annotations were in the zone, but well, that's maybe for a future project. And as we watch it build these 3 items, it should stop after this one. And there we have it. So what did we just create? Well, I created a folder called libraries, and in my blind flange library, I have all of my parts and all of my drawings in a separate subfolder. All right, now this would have ran everything in about 30 minutes, give or take. But I'm not interacting with that during those 30 minutes. I'm maybe taking my lunch break, having a nice poolside drink, whatever it might be. But we'll go ahead and close this out here just to move on to, let's go back to our PowerPoint. So macro, you may have seen, I didn't really describe it too much, but a macro is really just an automated function that imitates some action, some keystrokes. It could be a sequence of functions, but mostly we want to keep it nice and simple, and we want to make sure that task does that task really well without complicating and adding additional tasks. Don't make it too complicated, all right? So that's really everything on looped model generation. Now we can take a look at generative assembly modeling, and this pairs actually really well with looped model generation. So generative assembly modeling, like I said, allows us to build parts from uncaptured data, build assemblies from uncaptured data. In general, there are 3 approaches to automated modeling, not just in generative assembly modeling either, but to understand that better, we have a fixed list of parts that this could be. So all the components already exist as individual models. Then we can just use generative modeling to insert that part into a blank assembly, which we'll do. So this is very similar to, we can generate the fixed list similarly to how we generated the fixed list of all those flanges. But this time we'll use it for some button head screws, different screw types, different fasteners here this time. We can also generate on demand, which means that all components are created as new components and duplicates are allowed. So regardless of whether the file exists or not, regardless if this is a duplicate or not, we're always going to let them run this. Maybe it's because this job is unique to the customer and we want to make sure the customer has their unique location, their unique file, whatever it might be. But their on-demand still is very common, where we're executing just one component at a time and kind of going from there. And then there's a hybrid approach, where if these files exist, use the files that already exist, but if not, we want to go ahead and create the files and drive the files. And next time, we want to use that file from there on out. All right, so it's a sort of growing list of things. And this helps, this is probably optimal in most environments. This helps to keep things nice and lean in your vaults and file systems. So when reusing files, there are 2 cases that we need to stand by. First, we need to make sure that the folder location is the same every time and that the name is the same every time. So the file name of this washer, it lives in this folder. We can call this that standards folder. We also might have a separate custom folder where we store everything else. We can do so, we can create generative assembly modeling and through a DriveWorks technology called generation tasks. The generation tasks pane exists in stage 4 of the output rules. And you'll see here that I have my blank canvas. All right, this is an assembly with no parts or anything in it. Everything is going to be generated into this assembly. And the next thing to focus on is this generation sequence, this list of different tasks that can collapse and expand. The main focus of this generation is this main drive sequence. And everything else, all those other rules and part of the sequence are based around this main drive sequence where we apply the model rules and we drive layers and rename dimensions, everything that we've really set up in our model rules. Then we have our pre-main drive sequence tasks, and they're split up into 5 or 6 different tasks that, maybe we'll insert a task in any one of those depending on how we want this task to behave, or post-drive tasks. And in my case, it really doesn't matter where I put what, because the main drive sequence is actually not driving anything. It's really just renaming my assembly. So really, whether it's pre-drive or post-drive, it's all kind of happening in the same sequence. So with its pre-drive tasks, I split this up so it's a little bit easier to look at and understand. The pre-drive tasks allow us to insert the correct screw that's been generated from the fixed list. It allows us to then mate this screw so that it's fixed on the planes of the assembly. And then what we'll do is we'll open a file, the washer file and the nut file, and we'll save those as new washers, new nuts if they haven't been generated yet. From there, we can then insert the washer into the assembly. And once they're inserted as a post-drive task, we then drive dimensions using these generative tasks, drive single, drive multiple dimensions. And then from there, it'll go ahead and assign mates to these objects, to this component, to build out what we see here. So before we get a look at how everything works, let's just take a look at how we would rebuild this. So I'll go ahead and pull up or how we would build an assembly. So I'll go ahead and I can choose between different types here. You could have this look any sort of different ways. Here I'll go ahead and select Torx, and you can choose between M4 or M5. And all of these are just different available lengths that are at my disposal based off of the table data itself. So this is actually going off of a similar table as the blind flange data. Any of these options should automatically be generated if it's in this list. And that's the nice part about this type of list, is that it sorts based off of what my previous selections are. Anyways, I digress a little bit here. We can go ahead and also add washers and nuts. And the beauty of this generation task is that I could have, in theory, I could have 10, 20, 100 different washers, none of them captured, and I could still drive the inside diameter of the washer, because all it really is an address to the dimension change. So I can generatively generate these washers without needing to capture them, and that's really the power behind that. If you are a DriveWorks user, you know just how time consuming that can be when you're capturing so many parts. But here we'll go ahead and we'll select the basic types here. Optionally, if I wanted to include the full thread data, I could do that, which basically it would make it slower for me, but I don't need that. So I'm just gonna go ahead and hit generate. And it will go in and follow those same tasks. All right, let's go ahead and take a look at how that turned out. All right, so this looks pretty good, right? I got all my dimensions, all of these dimensions have been rewritten. And if I want, I could just unsuppress the thread data if I wanted to show that as well, because all it's doing is suppressing it. All right, and well, my form is pretty simple in this here. Like I said, this could be limitless, really, with how many different parts that we have there, as long as our naming mechanism, or as long as our part naming is logically and rule-based enough to make sure that these are inserting correctly. So there's a technique, but it certainly is flexible in how you build that. Anyways, we'll go ahead and close this out here now. Let's go back to the PowerPoint. Oh, that's actually, sorry, let's not quite go back to the PowerPoint. Let's talk about how it worked. Okay, so the first thing I want to talk about is the generation task sequence itself. Let's make sure I'm in the right project here. So to create a generation task sequence, I can just choose from my toolbox where I want to go ahead and create that. So whether it's insert part or drive a single dimension. Here I'll just drive a single dimension just because that's what we were talking about before. So I'll drag this into place, and for the dimension name, all I'm going to do is I'm going to format it so that it's going to be ID. Oops, let's make sure I type a text string at sketch 1 and then I have my part name, which is guised with this variable called no space sizing, and washer.part. Okay, so it has to be typed like this, .part, not SLD.PRT. We'll go ahead and click OK, and then the other thing is just the value. So here I'll go if this M4 size is equal to M4 by 07, then we'll use 4.3, otherwise we'll use 5.3. Okay, since we only have two options there anyway. So that would be how we would write a rule that maps this basic dimension. We can also add a condition that says we only want this condition to execute if there is a washer included. So I'll just find my washer, I'll double click this, and I'll click OK. So now it's saying if add washer return is checked on my form, this will execute this rule. The other aspect of it is just releasing the model, which is simply in the state here. All we need to do is release the blank canvas where those generation tests are associated, thus allowing us to build out the model the way that we would. So that is generation tests. Again, extremely powerful tool. Now let's talk a little bit about automated product documentation. This is really, you can really take your parts, your automation to the next level by creating spec sheets. How do we create spec sheets easily? Well, we can create spec sheets in Word that look very good, that match your product marketing standards. Like, for example, all of these fonts are GoEngineer's default fonts. Calling out this document here, we can turn a document that looks like this here into this here. All automatic. This could be generated en masse with the rest of the flanges or on demand, however you'd like. But let's start to talk a little bit about this technology. First, we can screenshot and embed the part, the exact part. This isn't just a default part that every model gets. This is the part, the BF15005 part. And then we can embed that in the Word document. We'll be able to create rule-based model parameters and custom properties and map those to things on this spec sheet. And we can export those as Word documents, as PDFs, or HTML documents. Well, actually, not with the images, but for rule-based model parameters, really easy to just create what are called bookmarks that will let us find or tie a model rule to this highlighted text here. So what to do there, we simply just highlight and then go to insert on our Word tab and find bookmark, and we'll give it a name and kind of go from there. Now when we load this up in DriveWorks, it'll see that name and you can build a model rule towards it. For the screenshotting process, there's a couple of different steps that we've already talked about for the technology behind how this works. First, in Word, we have to draw a shape approximately the same size as the scale of the image. And then we go into our selection. We go from shape format into our selection pane, and we give that a name. We'll call this insert part. So we're naming the shape. From there, we can go into a generation task called create image that allows us to take a screenshot of the isometric view of the part and save that to a location. From now that we have the screenshot generated, we want to make sure that that we can insert that, embed that into the Word document. So a macro from the specification power pack, a plugin that you can download for free on DriveWorks website if you have DriveWorks Pro, that is, that allows us to replace the shape with an image in the Word doc. First, I need the path to the custom Word doc. It's not the master path, it's the one that is generated from the specification. Then we'll need the title of the inserted shape, followed by the path to the screenshotted image. So again, very easy to build. I don't have to do any coding. This is just, it's basic Excel function, similar to basic Excel functions. So what do we get when we save this? My animations maybe don't look the greatest, but well, for generating the flange models, the manual effort to make a change to 8 or 9 dimensions, make a change to all of those custom properties and whatnot, 5 minutes would really be conservative. It probably would take some users 10 to 15, but with depending, it would probably take me 5 to 10. So we'll go in the low effort of that. If I was to manually build these flange models, all right, it takes me 5 minutes to do each one, and there's 117 of those. That means that's going to take me almost 10 hours to build all those flange models, working bell to bell. The effort to automate the same flange model was about an hour and a half. And the effort after automation was just a minute. So it doesn't really affect our time really at all. And that means that I can do all of these parts in just an hour and a half, which saves me 8.25 hours or 85% time savings from generating those models. And that's just the models. That's not the drawings. That's not the product specification sheet. Pretty insane, right? For on-demand generation, for that hardware assembleizer, it's kind of hard to estimate. I call it the assembleizer. I know that's not a word, but it's kind of hard to estimate because there's really no distinct file quantity. It could be an infinite amount of files, right? So while the manual effort might be 5 minutes to build the subassembly that looks like that, the effort to automate was definitely harder because generation tests, they're not easy to build right. A lot of times the syntax gets wrong, whatever it might be, but it takes a little bit longer to make sure it's just right. But like I said, over an infinite amount of file quantities, you can imagine just how much time savings that really is. There's really no number to represent that time savings because it's just a matter of when we'll break even, which will be inevitable. And then the product specification sheet, the manual effort to add all those, to take screenshots and embed all of those, and make sure everything looks nicely. Takes a while, probably 10 minutes, right? The effort to automate that only took me about 4 hours, and that's being pretty generous. And after that, it's all in mass generation. And again, we're saving 15.5 hours or 80% of our time. What would you do with 30 hours of your work life back? It can be, pretty astounding what automation can do for you. Now, I wanted to talk about one last concept that doesn't necessarily save time. Well, it can, for sure, but can be integrated with all your other projects, could be integrated with any of the projects that you see here, custom web requests. Custom web requests allow us to do a plethora of different things, basically pass data and send and receive data using these web service requests. Basically, we can just contact the cloud and integrate with cloud servers through REST API, GET requests, POST requests to obtain information, send login credentials to access that information, and do so securely in an automated process. Custom web request is pretty easy to build. One of the examples, unfortunately, I wasn't able to get this built into the system quite yet because I'm waiting on credentials, but this here uses a URL to access credentials to the closed API service. So I'd send an authentication with my username and password. And looking at the login request, we have a constant name right here. Let me add right? And this constant allows me to save the response that I get into that value. The get product information is where I actually want to get the price of an item. So I want to get the price of a fastener from my vendor, and I want that to automatically batch through there. Here I could simply add the request URL that accesses that port, provide my get request verb as well as my vendor part number, and then it would return again in a constant where eventually I will need to parse that big JSON response. That sounds really hard, Jordan. How do we parse a big JSON response? Well, it's really not at all. I was blown away by how easy it is. With parsing the data, all I simply call on is this function called XPathJSONGet. I call it the constant where we wrote that, and followed by the header price, which will return that price. Again, this could be added en masse and integrated to any of the solutions that we've seen through product documentation. Make sure that that price is actually accurate according to those documents. So there we have it. Let me turn off my laser pointer. We've covered a wide variety of different concepts. Let's just highlight those a little bit more. With design automation, there are 3 methods of design automation, the main one being rule-based design. Building on top of that would be master modeling. And on top of that, it's a generative modeling, only available through DriveWorks. So just keep in mind, that DriveWorks is the only option that allows us to generatively model those. Whereas if you're just master modeling and you're not having performance issues, it's very possible that SolidWorks and Excel might work okay. But for those other solutions like looped model generation, where we can rely on DriveWorks Pro and AutoPilot to generate this table of data and release those as parts, as opposed to just configurations, which is where SolidWorks limitations had lied. Then we have generative assembly modeling. And again, this is where we can store any uncaptured data. We can capture, or we can basically insert data that's not been captured. And how we work with that data depends on whether we want a fixed list of standard parts, a on-demand, or a more hybrid approach. And we covered automatic product documentation, where we got a beautiful form that looks like this. You could build 114 of these, or 117, excuse me, of these to match our product specs, all automatically. Save that as Word or PDF. And of course, we have our custom web request, which helps us send and receive data all the way back onto our machines securely over web services. And if all of this is possible with DriveWorks Pro, what else is? I'll leave that to you to find out. And with that, I'll take some questions.